Hello everyone, welcome to topic 7.7, calculating equilibrium concentrations. By the end of this, you should be able to identify the concentrations or partial pressures of chemical species at equilibrium based on the initial conditions and equilibrium constant. So given the stoichiometry of a reaction and the associated K value at a particular temperature, we can determine the concentrations of products or reactants for a reaction at equilibrium based off of the initial values of the reacting species. The concept behind this is essentially stoichiometry for reactions that don't go to completion. This accounts for the nature of equilibrium being dynamic, forward and backward reaction happening simultaneously, and allows for us to determine the final amounts of products and reactants. So one way to approach these types of problems is to use an ICE table. You may also see RICE table, where R actually stands for reaction, because as we will see, the reaction is needed in this. So ICE or RICE, either one's fine. So use an ICE table to organize the information in an equilibrium problem, where the I stands for initial, C stands for change with the coefficient, and E stands for equilibrium. Okay, we can use ICE tables for lots of different types of problems. Please remember back to when we covered BCA tables. BCA tables are a variation on ICE tables. Whereas in BCA tables you used only moles, ICE tables you will use concentration or partial pressures. So for example, given the reaction here, if your initial concentration of A and B is 1 molar, and the equilibrium concentration of C is 0.12 molar, what is the value for the Kc? So your first step is to write the Kc expression, so the equilibrium constant expression. So it's always products, so that is C to the 4th power over reactants, so A times B squared. And then set up the table. So we set up our ICE table, ICE, and then our reaction across the top, where our reacting arrow would be here. Okay, you write what you were given in the problem. Okay, since we have no information about the initial value of C, we can assume that that is going to be 0. By filling in the initial value, we know how much it is changing. Okay, but it's always going to change by its stoichiometric ratio. So 4 goes into 0.12, 0.030 times. So that when I add 0 and the change value, it equals my equilibrium. So we know what the change is. And that change is going to also be reflected through the rest of these. So this should be plus 4. Okay, this should be minus 2 and minus 1. And then the 0.030 is the proportion amount that is reacting. So then we can solve for our equilibrium amounts, and this should be 0.970 molar, and this one is 0.940 molar. So now we know how much we have at equilibrium. We can plug them into the equilibrium expression we wrote prior, which I'm going to rewrite here. So I'm going to plug in the values for A, B, and C. So C is 0.124, or 20, my apologies, to the 4th power. And then on the bottom is A times B squared. Okay, and then we continue to solve, so we're going to plug this into a calculator, and it'll spit out some numbers at us, and you should get, so try it just to check and make sure you're putting it in right. So when you put it into your calculator, do this to the 4th power, divided by this and hit the equal sign. So this and then hit the equal sign. Then divided by the A concentration and hit the equal sign. And then divide it again, because it's still in the denominator. This number is in the denominator, so hit the division sign. And then parentheses, this number squared, then close the parentheses. So the square should actually be on the inside of the parentheses when you put it in your calculator. And then hit the equal, and you should get this. Or set up your calculator expression using lots of parentheses to get it all at once. You just got to make sure you're telling it what needs to be in the denominator, so you're not accidentally multiplying by b. So in another example, we are provided with a value of K and the initial concentrations and have to find the equilibrium concentrations. We can also use an ICE table to solve this type of problem. So given that A plus B yields AB with an equilibrium constant of this, if 1 molar A and 2 molar B are allowed to reach equilibrium, what are the equilibrium values? So you first start again by writing KC expression, so that is products, which is AB, and there are no coefficients because it's all a 1-to-1 ratio, so we do not need exponents because they're all 1. And then fill in the table with what you know. Okay, then you will have to set up these tables, and a lot of times I write the reaction, and then I write ICE on the side. Draw a line between I and E, because that way I know I plus C has to equal E. And then I draw a double line underneath the arrow and single lines between all the reactants and products. Okay, so the double line separates my reactants from my products, and then the single line separates species on the same side. So since we know that AB, the product, there isn't any initially, we can say that's 0. We know that this reaction has to produce products, so we know we're going to add products. So we must then use reactants. And we don't know by how much it's going to change, so we're going to call that X. And we're going to use the equilibrium constant given and the expression to solve for X. So 1.00 minus X when I add these together. 2.00 minus X. And then this one is just X. Okay. If I have coefficients, then the coefficients are utilized here and distribute to the X. We then can complete the equilibrium values in terms of X, in terms of X. Finally, we're going to plug those in to the equilibrium expression that we wrote above and solve. And there's 2 ways to solve. Okay, you can either use the solver function or quadratic formula in your table. This is a lot of math. All of the ones on the AP test should be able to be solved easily using a standard way of solving, or be able to use the assumption-based solving, which says that we assume that X is super, super small. That's because we have a very small Kc value, which is at least 10 to the negative 3 is a good start, and this is 10 to the negative 3. Because Kc is small, we say that the change is going to be small, so X is super small. So we end up making an assumption, and I'll go through that. So when we do the standard way of solving and set up our K value, which Kc is equal to X over 1 minus X times 2 minus X using our equilibrium values up here. and that has to equal 0.0034, which is 3 times 10 to the 3.4 times 10 to the negative 3, which was our equilibrium constant given. If we rearrange this to set it equal to 0, or you can, if you have a solver, you can just enter this into your solver on your calculator. Okay, not being a math teacher, I don't know where that is, but we can find some videos if you ask me for it. I hard mathed this using really hard math that, and got this one. A good solver, if you don't know how to use the one on your calculator, is Wolfram Alpha. If you get it set up, it'll help you solve for the x values when the approximation method doesn't work. Okay. But I love the approximation method. Well, what is that, Ms. Burt? Well, I'm going to tell you. So x over 1 minus x times 2 minus x. So this says that the change in x is very small. So when we are subtracting or adding it to another number, that tells us that that is not going to change that number significantly. Okay, so we can say that that x, that one there is going to be approximated to 0, and this one will be 0. So we can write our assumption Kc as x over 1 times 2, because we said that those x's that were being subtracted are very, very close to 0, that change is very, very small. Okay, and so that has to be equal to 0.0034. When I solve for x, I end up seeing that x is equal to 0.0068 molar. And if we compare this value to this value, the assumption value, the assumption 1, works. It is dang near the same, so it is a good assumption. So we can use either one. I'm going to actually use the assumption-based value because it works and makes me happy. So, okay, so now that we know x, we can plug it back into the equilibrium concentrations we determined containing x. So 1.00 minus my x, 2.00 minus x, and then x, we end up getting 0.99 because of sig figs, and then over here 1.99. And notice the change is so small that it's not impacting those. And then 6.8 times 10 to the negative 3 molar in scientific notation, because why not? Why not? Okay, so while these are a little finicky, the assumption-based solving is a good tool. Being able to use your graphing calculator solver is great, but on the AP test, whatever you're given will be simple enough to solve using either the standard way or the assumption-based solving, okay? Some of the practice problems you guys will do, you'll want to use the solver in the UDO, because the assumption-based solving doesn't quite work. But those are challenging to get you in the habit of practicing and working out those problems and thinking them through. Okay, so that way when you're faced one on the AP test, it is not a surprise and it is easy to tackle. So let's go over this I do. So consider the reaction given. Enough ICl was added to reach a partial pressure of 2.45 atmospheres in a previously evacuated vessel. After the reaction reaches equilibrium, the pressure of the I2 in the system was 0.30 atm. Complete nice table to show how to find the equilibrium pressures of each. complete an ice diagram to find the equilibrium pressures of each species and then use those values to calculate the value of the equilibrium constant. So we're going to plug in what we know. So we know initially I have 2.45 atmospheres of ICL. And then I know at equilibrium I have 0.30 atm. Using stoichiometry, I know that I should have the same amount as this because they have the same stoichiometric ratio of 1 to 1. So whatever I make of one, I have to make of the other. Okay, so knowing that, I also know that this is 0 at the beginning, and that the change, since I'm shifting towards the reactants, I'm going to make reactants, so plus their coefficient times whatever change value. And then I'm going to use the product, but it's got a 2, so I'm going to bring the 2 down, so the coefficient times the change value. I know 0 plus whatever has to give me 0.3, so I know that this has to be 0.3 all the way across, because the change value does not change. It is how much you're changing the whole reaction. So it's the same for all species in the reaction. The coefficient and the direction of the reaction will change the sign and the magnitude and keep it stoichiometrically the same or balanced. So then solving for the equilibrium pressure of ICL, we do 2.45 minus 2 times 0.3, and you should get 1.85 atmospheres. So now that we have our equilibrium concentrations, we can calculate Kp. So start by writing the Kp expression, which is product, so pressure of ICL, and it is got a coefficient of 2, so it is squared, over the pressure of I2 times the pressure of Cl2. And so now that I have that, I can substitute in my equilibrium pressures. So 1.85 atmospheres squared over 0.30 atm times 0.30 atm. So now we are going to solve this one. So Kp then, when I plug these values into my calculator, I get 38 because of sig figs. And so that is my answer for the I do. Okay, so now we're going to look at the we do. So considering this reaction, the reaction mixture initially contains partial pressures of nitrogen dioxide at 0.1 atmosphere. When the reaction reaches equilibrium, it is down to 0.008. Find the equilibrium concentration of N2O4 at this temperature and use it to find the equilibrium constant. So one of our first steps is to write the equilibrium expression. So that is going to be the pressure of NO2, because I'm given pressure units and these are gases, squared, because that is squared, over the pressure of N2O4. Now that I have that, I can set up my ice table. So I write my reaction. And then I write my ice, ICE. I draw a line to separate E from C, so I know that these are going to add to give me E, and a double line underneath the arrow. I don't have additional reactant or product species, so I don't need single lines. Now I'm going to fill in what I was given. So I know at the beginning it tells me I have a partial pressure of 1.100 of this one. And then at equilibrium, I have 0.080 atm here. It doesn't tell me anything about N2O4, so I'm going to assume that I start with nothing there. Now I know that I then have to make some of the N2O4, so I write the plus sign to indicate that. And I'm going to use, and I see that it decreases, so that reinforces that. I'm going to use the NO2, and I'm going to bring the coefficient down for the change Now I have to figure out how it's changing. Okay, so 0.1 minus 2 times something gives me this. So that means that this is equal to, so 2 times something gives me this value. I'm going to divide this then by 2 to give me 0.010. Okay, and since this is how the reaction is changing, everything has to change like that. So everything in my parentheses is going to be there. So then I'm going to do 0 plus 1 times this value, and so that gives me the equilibrium partial pressure for N2O4. So now that I know the equilibrium partial pressures for all the species in the reaction, I can use my Kp to solve. So I'm going to plug in here the product, so 0.080 atm squared over my reactant, which is 0.010 atm. Not squared or anything because it has a coefficient of 1. And solving for this, I get 0.64 for my equilibrium constant. Okay, so this concludes the notes. Complete the you do. Check your work. Use a solver either in your graphing calculator or like Wolfram Alpha. Once you have the equilibrium expression set up to help you, if you find that you cannot use the approximation, like this one, I would say you can't use the approximation method, but I would say on this one you can use the approximation method given how small it is. Okay, so thank you for tuning in. Check your work as you go for the you-dos, and have a great night.